Thank you for having me here. So my presentation title is Responsible AI Engineering. So I would like to discuss or introduce our team's work on responsible AI, how to implement responsible AI from a system perspective. And my name is Qinghua LU. I'm a researcher from CSIRO. I also lead the responsible AI science team at Data61. So before I start, just want to quickly introduce my organization and team. So we just had a discussion on the organization. CSIRO is Australia's national science agency, and it has like a 100-year history. Now the organization has around 5,000 people, I think based in 50 sites across Australia. Also, we have offices in other countries like France, Chile, US, Singapore. And Data61 is one of the, I think, 9 research business units in CSIRO. And the responsible AI team is a relatively new team in CSIRO. We formed this team in 2022. Now we have 30 full-time researchers and engineers in the team. And 6 of my colleagues are now included in the top 30 researchers for responsible AI globally, according to their Google Scholar citations. And on the right side, you can see the books. One is a new book on responsible AI. We published this book last December, and it was ranked the 3rd place in AI category on Amazon website, I think 2 months ago. And another book, we are still working on that, is about AI engineering. So we will discuss the challenges of different software qualities and how to address these quality challenges from architecture and DevOps perspective. And a bit background and context for our team's work. So for this slide is just the definition about AI system AI. So the first definition is from OECD. This is a new version. So you can see AI system is a machine-based system that use the input to infer or about how to generate output. For example, predictions, contents, recommendations, decisions. So here you can see this version include content. So this like in response to the generative AI concept. And because and here we use infer as a verb, not computation. So there will be more uncertainties in AI system. And the definition about AI is pretty simple. So just research and development of mechanisms and applications of AI systems. So this one is from ISO standard. Then the definition about responsible AI. So this one is from our book. So you can see our perspective is a system perspective. So we emphasize it's about the development and use of AI systems. And here we not only discuss the negative risk of AI system, but also we think responsible AI should also cover like positive opportunities. And I will later introduce a framework from our team called ESG AI framework. So we will provide like an analysis of both positive opportunities and negative risk for different AI applications in different domains. And this diagram shows like ecosystem of AI. So you can see there are different stakeholders. At the top is AI partner. For example, the AI related service providers like data providers. And the data can be used for training the narrow model or foundation model. It can be also used as input data for the AI system. And then the output data could be used by the AI partner for other purposes. Then in the middle, we have AI producers. So they are the one who is responsible for developing models or systems. And the narrow models or foundation models, they will be integrated into the AI system. And the foundation model, they can interact or work with narrow model and non-AI components. and the output will be sent to AI users. And some tasks might affect the external entities, for example, the environment, communities, or the whole society. And the bottom layer is AI components, platforms, and tools. So they are provided by AI providers. So AI providers are like AI service providers. And this layer is also relevant to AI deployers. So the AI deployers will deploy the AI system, make it available to their internal or external users. So that's the AI stakeholders and their relationships. Then talking about trends and the challenges, so there's a trend here. We want to highlight this trend, like from small model to large model, then to compound AI system. So maybe you have heard about end-to-end AI. So it's just the system will have like only one AI model. So the input will be the data, then the decision will be the output, and there's no non-AI component outside the model. So that would be maybe the end of this trend. And the left side figure shows a traditional AI system. So the brown or yellow boxes here are AI models, for example, detection models, planning models. Then the green boxes are non-AI components, the software code. The current situation is like we use the foundation model as a main component in the system. So you can see the green layer is getting very thin. So that means we only need very few components, non-AI components outside the model. And early this year, I think AI Lab in Berkeley University, so they published a paper about the shift from models to compound AI system. So from their definition, you can see the compound AI system is not only about foundation models or AI models. So there could be other components like data retriever or external tools, safety or guardrail components. Then there's the engineering gap in this in the responsible AI area we have defined. So here in the middle, you can see this quote from our customers. So they complain they know like senior management is called for responsible AI, but in practice they don't have any concrete guidance or tools for them to use to build the responsible AI systems like the AI chatbot. So that becomes our motivation for responsible AI engineering. And we know to implement responsible AI, many organizations and countries, they release different versions of AI ethics principles. For example, Australia has released 8 ethics principles I think back in 2019. Then this year, Data 61 is also contributing to the development of Australia's AI safety standard. And there are other standards like ISO standards, NIST standards, OECD principles. But here we like to argue the principles or standards, they are not equal to engineering practices. And on the other hand, there have been many efforts on model alignment or model fairness detection tools, but they are not equal to system alignment. And the model at the end, they need to be integrated into a software, and it's a software which will be deployed in real world and have the real world impact. So that's a motivation for us to look at the middle part. So how to work on the system level challenges. And this slide, because data is quite important component in AI systems, so we also identified several major data-related challenges. For example, the training stage for the training data, there could be distributed trust. So if the analytics is across different organizations, across different devices, so how can we build the trust without directly seeing the data? Then the next challenge is about zero trust. So the unsupervised learning may use like online well data. So there could be data poisoning issues. So how can we track the poison data or find out the source for this data? So it could be a challenge. Then the next one is trusted license. So it's not just about the ownership or copyright of the data. It's more about like how to how to manage the use of the data, how to manage the or how to monetize the data. So here the third challenge we summarize is trusted license. Then the last one is trusted artificial. So synthetic data could be very useful to like address the data scarcity or data privacy issues. But there could be an issue like whether the synthetic data will reflect the real world challenges or real world distribution. So this one is a fourth challenge we have identified. Then for evaluation data or evaluation stage, the first challenge is trust in evaluation data. So there could be the data linking problem. So we need to make sure that evaluation data does not appear in training data. And talking about human feedback, it's not always reliable. So we need to also evaluate the quality of the human feedback in the testing stage. Then for system level data, there could be challenge about trusted knowledge. So there might be inconsistency about the different data sources. Or between the external data source and AI knowledge. And also there are challenges about the trade-off. Maybe it's not always about optimizing one dimension. So there could be trade-offs between fairness and privacy or accuracy. Then the last group of challenges is about generated data. So we need to make sure the ground truth data is always up to date, and we should make sure the provenance of the data using like watermarking or fingerprinting techniques. So then I want to talk about how to close the gap, how to fill the gap through the responsible AI engineering approach. So we have just discussed like we need system level. We need to like work on approach to address system level challenges. So in our work, we call it responsible AI engineering approach, and which includes three perspectives. The first perspective is governance perspective, like how to build industry level governance, how to build organization level, and how to achieve it at a team level. Then from the development process perspective, what are the available best practice or tools for different stages of engineering lifecycle? And the third perspective is a system perspective or product perspective. Like we need to think about what are the design patterns, how we can build a responsible AI into the architecture, what are the system level techniques to ensure responsible AI. And of course, trustworthiness is not equal to trust. So how can we build trust through the different mechanisms of design patterns? Then in our team, we have two groups of solutions. The first group is about methods and best practice. So I will go through the details in the later slides. But you can see the question bank is for assessing AI risk. The matrix catalog is more about how to concretely measure the AI risk. Then pattern catalog is reusable solutions to mitigate the risk. Then the last part is about reference architecture and taxonomies, about the agent design, about AI evaluation. So they can be also considered as high-level guidance. And the second group is about the tools platforms. So we have different tools for risk assessment. Like for managing AI supply chain risk or for investors to understand the risk. And also we have been working on an engineering platform for creating personalized agents. Now we are working on the runtime features, adding guardrails into the runtime loop, and also build the context management functions to support more proactive suggestions. So this one is the first framework we have been working on. So it's a responsible AI question bank. The current version includes 300 questions for understanding AI risk. So we have the high-level principles. So you can see from this diagram, in Australia, we have like 8 principles. Then for each principle, we have identified categories and subcategories, and also summarize or identify the questions. We didn't create those questions. It's actually based on the results of a mapping study. So in that mapping study, we examined, I think, 16 frameworks, and we extracted the questions as a checklist for different principles categories. And this one is metrics catalog. So I mentioned the main motivation is we don't want to rely on humans' subjective expertise. So we want to have like more concrete metrics for AI assessment or AI risk assessment. And there are 3 types of metrics in our work. The first type is process metrics. It's like is there a risk assessment committee in the organization? So that could be a process metric. And we could also have resource metrics. So that's the tool that can be used in the process. Then we have the product metrics. So it's like the output from the process. And this table is like the accountability metrics. So we highlight, for example, auditability is one of the accountability criteria. And we have like data provenance, model provenance, system provenance in this category, so as the process metrics. And we have the key considerations. So they can be used to assess the quality of the process. For example, if the company has a risk committee for AI, but how about the committee members' background? Do they have sufficient responsible AI capabilities? So that could be considered as key consideration factors here. And also we identify resource metrics and product metrics to support like more comprehensive assessment. And this year we released a framework about ESG AI assessment. And for organizations, when they think about or consider to develop the AI risk framework, they usually ask the question like whether to use their existing framework, extend their existing framework, or they want to create a new framework. So we found that based on the engagement study, we think we interviewed more than 30 global local companies in Australia. So we found they usually use ESG framework to manage the sustainability risk. And then we decided maybe we can see obviously there are like overlaps between ESG framework and the AI ethics principles. And this diagram actually shows the mapping we have done. So after this mapping, we have built this framework, including 3 components. So for the investors or ESG managers in the organization, so they could first look at the AI use case. We have summarized 9 domains, and we selected top AI applications, 3 top AI applications for each of the domains. Then for these AI use cases or AI applications, we analyze the risk and opportunities. Then the second step is AI governance indicators. So it includes 10 high-level indicators. So because in step 1, we have done the mapping to EU AI Act, so we know like which AI use cases have high risk, then if one company has high risk application and also the company's governance score is quite low based on the step 2 assessment, then we can go to the step 3 deep dive assessment. So it will include 42 sub questions for the 8 leading principle based question. So we can review the governance process or review the development process in the organization. So once we've done the AI risk assessment part, we need to mitigate the risk. Here we have adopted a pattern-oriented approach. So in software engineering, pattern is a reusable solution to a recurring problem in a given context. But here we extended the scope. It's not only about design pattern. It's also we also called process best practice or governance mechanism as patterns. So the right side of this diagram, you can see the structure of the pattern catalog. And the current version include, I think, more than 60 patterns for different perspective, like the governance process and product. And on the right side, you can see one example of the pattern. So it's like a structured knowledge base. So we have used the traditional design pattern template to describe the best practice, but we also added additional fields. For example, we also have like type of pattern, type of objective, whether it's designed for improving trustworthiness or trust, and target users who will use this pattern. Is it software developers or software architects, data scientists, and who will be impacted by this pattern, impacted stakeholders, the relevant principles, and also life cycle stages. And also we have like map these patterns to EU AI Act or ISO standard. So in the pattern template, we always have the context, problem details, also solution details, analyzing the best benefits, drawbacks. So it's not just about the benefits. So sometimes the pattern may introduce new risk. So it would be useful to have the drawbacks analysis here for the pattern description. And for known uses, they are the existing application of this pattern. So people can know which application has adopted this pattern. And this slide is just about governance patterns we have collected. So you can see industry level, we have collected maybe 10 patterns, and organization level, team level. So I highlighted some patterns, just want to show they are not isolated. So we want to make the patterns interconnected. So for example, to achieve the industry level pattern, we may have some organization level pattern to support. Then team level pattern, what kind of pattern we could have to support the organization level pattern. And also for the process pattern and product pattern, we also have relevant patterns. So they are like connected across layers or across different types. And for process pattern, is based on the development life cycle. So requirements, we have identified a list of best practice, we call them patterns here, then design, implementation, testing, operation. So they can, people will know like which stage, what kind of patterns are available here. Then product pattern is more about the components or architectural structure in the AI products. So we claim if you use this pattern, you are building responsible AI into the design, then your product will have the responsible AI elements or features, so it can become your product's competitive advantage. And for this system reference architecture, so we embed the patterns into the architecture, and also we have 3 layers. So it's not just a system layer. We also have the supply chain layer about developing or procuring the AI components or non-AI components. The operation infrastructure is about monitoring, tracing the evolution of the components. or input or output from the components. And from last year, I think after the release of ChatGPT, so we also moved to foundation model based system research. So our first paper was about the reference architecture for building or designing foundation model-based systems. So you can see the architecture, we adapted the previous version, but we have identified like unique patterns for foundation model-based systems. For example, if you think about the growing capabilities of foundation models, so they might absorb some capabilities or functionalities of external components. So here we have one pattern called adapter, another pattern called microkernel. So we try to make each component's responsibility very minimal. So if this component is absorbed by the foundation model, or replaced by the foundation model, it will not affect the other components. And also operation layer, we have guardrails, black box recorder, so they can be used to make sure responsible AI when running the foundation model-based systems. And another work is taxonomy. So taxonomy is about like comparing or classifying different design options for designing systems. So we have like three categories here. First one is about pre-training and adaptation of foundation models. So there could be different pre-training types of pre-training data, and could be different ways to adapt the foundation model for downstream tasks, whether to use fine-tuning or in-context learning, distilling. And when build the system architecture, we need to understand what kind of roles the foundation model could play. So foundation model can be used as the software connector. So they can be a connector coordinating the workflow, connecting with different narrow model or non-AI component and complete the overall workflow. And how to integrate with local data, with organizations' local data, whether we use in context learning or we use retrieval augmented generation. So even the context size is becoming very large for some of the foundation models like Gemini. So it might be there might be some qualities about the context information. So it's still useful to use a RAG solution in the system design. And there have been different RAG design patterns, like a federated RAG for data analytics across different organizations. And for responsible AI, we have identified solutions at model level, system level. So just want to differentiate the types of solutions. And we have internally built a chatbot for analyzing responsible AI risk. So this tool is built on GPT-4, and the knowledge base behind the screen is the question and the manually labeled incident database. So you can see the stakeholders, they can ask questions about their AI applications. And on the right side, we share the intermediate process. I think, is there a question? So that's this question chatbot, answering chatbot. Then because agent is one of the foundation model system, it's just like autonomously achieve human goals through the agents. So we work on the architecture of the agents. So there could be two types of agents, coordinator agent or worker agent. So the human can send their goals to the coordinator agent, then the coordinator agent can suggest the plan or strategy to the users. Once it's approved, the coordinator, they can make the plan about the workflow and then connect or select different worker agents or different tools to complete the task. And this is a more detailed design. So we have like interaction engineering layer, which includes context engineering and prompt engineering. So context is important, very important for the large language model agent to understand the problems or humans' intentions. So here we have like two design patterns. One is passive goal creator. So it's like the users, they send the prompt to the agent, then the agent work out the workflow plan. Then we also identify another pattern called proactive goal creator. So based on the multi-model context information, the agent could guess the human's goal. So they can maybe retrieve the context information like the gestures from the users, or they can check the human's previous interactions with the computers. Then they can guess what this person be interested in as a next step. Then prompt engineering is about like integrating the context information into the prompt, and also makes the prompt more structured, easier for the large language model to understand. Then the next layer is memory layer. So the short-term memory could include like working context configuration or recent events. Then the long-term memory will be the past knowledge or experience. So it's quite important for the agent's learning, the long-term memory. So based on the past experience or past observations, the agent could maybe provide more reasonable suggestions. The next layer is planning layer. So as I said, they can make the plans and ask humans for feedback, for approval, and there could be plan reflection component here. So the agent could do self-critique their plan generated by the agent, or they could ask other agents to review the plan. They can ask the humans to review the plan. Once the plan is approved, the execution engine, next layer, will execute the task. And there could be different cooperation modes, like voting-based cooperation. So if they have different opinions among the agents, they could vote for the actions. Or there could be role-based cooperation. So some agents could be the project manager, some agents, they could be the developers or testers for software engineering tasks. And the agent, they can use or leverage the Axon tools to complete the task. So we might need some features to support the tool learning for the agent to use the tool more efficiently. And there could be some impact on the interface design. So because these days, the tools interface or APIs, they are designed for humans. But if the agent would be the future user for the tools, there could be some more research about the tool interface design for agents. And we have the responsible AI plugins at different layers. And last month, we released the pattern catalog for agent design. So it's a separate pattern catalog. Still, we use the template, pattern template to describe the solution, but the patterns about the how to design the agents. And you can see the details by visiting this link here. And for agent design, I think two most important thing, one is guardrails, the other one is evaluation. So guardrails, we have been working on taxonomy. So usually, if you look at the recent guardrail products or research work, they talk about the functional correctness of guardrails, like by using the guardrail, whether the sensitive information can be removed, or whether the prompt injection risk can be removed. But in our research, we argue there could be other quality attributes that are critical for designing guardrails, like customizability, generalizability, interpretability, etc. And also in terms of the action, it's not just input, output, filtering, or modifying. It can be other aspects involved, like the external tools. There could be vulnerabilities about the external tools or external narrow models. And there could be issues about the plan generated by the agent or the reasoning process generated by the agent. So it's not just about the input output. We want to have like more comprehensive guardrails design, and customizability is important. So we would like to provide like negotiable guardrails, also dynamic guardrails, so it can be continuously evaluated. So we have the evolution in the process. It's dynamic input. And of course, in terms of the model, it's just not just about text. It can be images as output or input, or videos as input output. So there could be dark patterns, for example, on the UI interface design generated by foundation models. So we should also think about the guardrails for multi-model systems. And in DataSys one, we have started an internal initiative called Science Digital. So we are building an agent platform. We have completed the design part. So that means the users or humans, they can use natural language to communicate their requirements. Then the platform will generate the form to extract the information, or also add like more information, more contact information to the forms for the large language model to understand. For example, on the left side, you can see the persona. We analyze what's the persona for this agent, what could be the audience for this agent, what are the roles for agents running. Then on the right side is like a Copilot chatbot. So the users could just communicate their requirements, their understanding about the agent. And also we can, this platform can visualize the workflow. So the users, they can drag and drop to adjust the order of the workflow of the steps. Then for runtime, we are still working on that. So we plan to add the context engineering part and also the guardrails, the continuous learning feature to the platform. Another important concept is evaluation. And we found the problem for AI evaluation is there are different communities working on AI evaluation, like AI community. So they work on model testing, model validation, and software engineering people, they work on software qualities of the AI systems. Then there's like AI policy community. So they talk about the risk assessment, impact assessment. So they have like also different interests. So we have recently worked on a paper called AI evaluation framework. So the first part is about the harmonized terminology. So we want to understand the evaluation terminology in different communities. And the evaluation is defined as the process of assessing AI models or AI system against specific criteria or benchmarks. And it can include both static evaluation and dynamic evaluation. So static evaluation could be risk assessment. You don't need to execute the artifact. And dynamic evaluation, you need to execute the task like the testing. And the evaluation should include both model and system evaluation, like we discussed, and include everything we have discussed in different communities, like testing, verification, validation, benchmarking, capability evaluation, also risk and impact assessment. And for what need to be evaluated. So it's not just about accuracy, statistical accuracy. It should be also including functional accuracy or functional correctness. How well the AI model achieve its task or meet its specified functional requirements or user expectation. Then for quality attributes, So we need to think about what are the immediate quality outcomes and also the long-term qualities like maintainability, sustainability. Then for risk, it's about the likelihood, also potential negative consequence of the event's actions within the AI system. Then for impact, so it's more about wider or longer term effects that AI system may have on the individuals, communities, and the society. Then for large language models based systems, so we often talk about the broader capabilities like goal seeking or tools capabilities. So there could be planned capabilities, so we need to evaluate, but there are also unplanned, dangerous emerging capabilities which require evaluation. And for the taxonomy, we have identified component level, system level. So for component level, in addition to non-AI component, AI component, we also have listed the guardrails. So whether the guardrails are sufficient. So this requires evaluation. So it's also aligned with the taxonomy work we have done. We need to evaluate not only about accuracy or functional correctness. We need to understand whether the guardrails is customizable or interpretable. So those are very important quality attributes to guardrail design. And for system level design, so we need to consider operational and the environmental context. They might have like specific requirements for AI systems. And this is a mapping of AI evaluation to life cycle stages, the stakeholders. So for example, for plan, the design stage, the AI producers, they need to do the impact assessment. Then for data collection stage, maybe it's AI partners' job to do the data evaluation. So we want to understand the responsibilities of different stakeholders in the AI supply chain. So to close the data gap, we have been working on privacy risk assessment tool called alpha, so they can understand what kind of data risk, especially data privacy risk, if the owner of the data, they share the data with other people. So we have identified like some metrics or factors, for example, to identify the identification problem. And then another work we have been working on is machine learning. So machine learning is about the right to be forgotten, but the owners of the data, they could decide maybe to get back their data from the model's training data, but there could be implications on the fairness part. So what could be the fairness implications of different machine learning methods? So we have published a paper talking about this problem. Then for the generated data, we can use watermarking, fingerprinting, or other mechanisms to trace the source or ensure the provenance of the data. But here, I think it's more about like when to apply these techniques. So whether it's, we should apply watermarking or labeling during the generation or after the generation, and how about the robustness? So is it easy to be removed, and or how we can protect the privacies? Then the last slide, I think here I have is about bill of material. It's for managing AI supply chain risk. So we have used blockchain to build the infrastructure for sharing the SBOM information. So the supply chain stakeholders, they can check the procured components AI risk stored on blockchain. So that's all about this talk. So we have been working on like system level challenges using the responsible AI engineering approach. And here we also think current focus is more on product level evaluation. Previously, we have developed different frameworks for AI governance, process, risk assessment frameworks. Thanks.
Many thanks to Qinghua for the presentations. The first question I would like to ask our speaker is that